Having discussed the equations of motions in terms of the form factors, we have implicitly traded into a domain of description that is little beyond the classical physics. So, what we have done is traded into the area of quantum domain, brought this conception here, and trying to use it to interpret our data. But more often than not, we are not very clear in our understanding or interpretation, that is, why something or some effect that is considered to be proportional to some powers of a tiny quantity, that is Planck's constant, should reproduce a result that is at the best follows from the tree level Lagrangian. Generally, what has been observed is in some limit the results of a quantum calculation reproduces the results of a classical calculation, or in this particular case the fluid dynamic equations or kinetic equations. I believe that this issue has not been investigated in its full depth, except on and off by researchers for some specific cases with their profound insight that shone some light. But more generally, it is to be done considering the case of, or considering the role of the statistical factors to the resolution of this conflict. Typically, the instruments of interest that is called the Feynman diagrams in a vacuum theory are not something that takes into account the many body effects. But when one considers the many body effects, then probably the number of quanta and the tiny constant that one talks about, the product when it behaves in a way such that this product is constant, whether the tiny amount goes to 0 or the large factor becomes larger or smaller, the product is always constant. Then it would give us a clue that why the one loop level results of thermal field theory are seen to reproduce the results of classical physics so close. Okay, leaving this observation aside, let us now go on to have a look at the equations that followed from the Lagrangian. Though we are not very explicit about how to get to these equations in terms of the form factors, I will just give certain clues over here. The clue is, one, in principle write down the equation those the vector quantities satisfy, and then multiply these equations by the unit vectors to project out the particular components. Those get coupled to each other, and as a result it is noticed that the parallel component of the photon's form factor and the perpendicular component of the photon's form factor remain coupled to each other if the associated part of the photon polarization tensor we have called pi p remains non-zero. You know, it may not be very out of place to bring out an issue here, and that issue is, in the case of electromagnetism, we have often come across things, those are called dielectric constant and permeability. Sometimes these are termed as the two electromagnetic constant, but there may exist a third one too, that is usually termed as the third electromagnetic constant. This pi p that you are shown in the transparency is related to this third electromagnetic constant, and due to its presence, any disturbance in the parallel direction as it propagates is going to be linked to a perpendicular. The a perpendicular one gets linked to the parallel one, and this whole exercise continues as the wave or the disturbance propagate in the medium. However, for the kind of interactions that we are interested in, the longitudinal part remains unaffected and it propagates actually. If we somehow could get rid of these form factors from the effective description of their propagation, the relationship that we will be left with is usually called a dispersion relation. And a dispersion relation has a property that it can tell you how fast a signal is propagating, whether it is group velocity wise or the phase velocity wise, and their departure. So, to calculate or to estimate that, what is necessary is to have a grip or understanding on the form factors. This is called pi transverse, pi longitudinal, and pi p, that is a polarized, these three. And as can be seen from the structure of these equations, where k square actually is a 4k square, that is difference between the energy square minus the wave vector square, and it depends on pi, be it pi L, pi T or pi P. So, the magnitude of pi T, pi L and pi P stands out to decide the size of the velocity, whether it is group velocity or phase velocity. That is in one area, and on the other side, the solutions when they are obtained from these equations, the solutions themselves also would depend on these magnitudes of these form factors. So, the spectropolarimetric observables do also depend on these form factors pi T, pi L and pi P. So, having talked about or bringing out the importance of these form factors in the relevant analysis of the physics, we need to pay our attention a little bit about how one actually identifies or characterizes a medium, whether it is classical, whether it is relativistic, whether it is ultra relativistic or degenerate or ultra degenerate. A system is usually called classical when the velocity scale associated or average velocity scale that is associated with the objects those make it up is small compared to the velocity of light, or so to speak, the momentum is small compared to the mass of the object. Now, before you start objections or raising objections, we are working in a natural system of units in which dimension of mass and dimension of energy are the same, and the other extra advantages. So, in such situation, you can actually weigh these two factors, and if m is contribution is more, we call it classical, where the relativistic effects become important when the contribution from the mass or energy scale associated with mass becomes subleading compared to other scales those are present in the system. So, in that case or in that situation, if you have velocities those are comparable to that of light and we can ignore the effect of mass, then we will call such a system as ultra relativistic. If they are close by, we will call them relativistic, and if the ensemble that the underlying media is made up of had finite chemical potential, we call it degenerate, and if the contribution of the chemical potential outweighs the same coming from mass, we call it ultra degenerate. In most of the ideal situations, one can take the classical limit of the distribution functions and carry out a calculation of following the classical techniques to draw conclusions about the spectropolarimetric observables, but when the system is close to that of a relativistic degenerate or ultra relativistic or ultra degenerate, then these approximations, there are situations where these approximations may break down. So, this is something that one should have to keep in one's mind while drawing conclusions about the size of the correction to the observables that they are looking for. Now, before letting the whole system move, that is considering the motion in 4 space-time dimension, it may not be bad or out of context to look into their behavior close to a situation that's termed usually quasi-static. That is, it's neither static exactly in space-time, nor it is moving with its typically assigned speed in space-time. And how do we get to that? We get to that by looking into the contribution that's coming from these form factors in 2 limits. One is when its energy is equal to 0, but the wave vector k is not exactly 0, it is approaching 0, and the other one is reverse of the same. And there are investigations that have been performed to establish the fact that these 2 limits are not commutative. Nonetheless, we will come back to this particular issue as we go along. Thank you.